We continue. Okay. So this will be a little bit more technical, but hopefully you'll enjoy what you see because it's also getting more interesting. So I want to talk about, again, Ginzburg-Landau. Theory, but with magnetic field. So let me first again think about classical mechanics. So this is classical mechanics. When you have like a charged particle, E, of course with mass, and you include electromagnetic field, and the way we incorporate electromagnetic field is with vector potential and scalar potential. Lagrangian is now going to be equal to 1/2 m v squared. Let me write it like v squared plus q over c v dot a minus, okay, the charge, let me keep it q to keep track of more general charge distributions. And this is q times phi. A and phi, they depend on r, but I'm not writing. They can also depend on time. That's allowed, right? That's fine. And here v is defined as dr dt. So this is vector potential. So this is scalar potential.
Isn't it curl of A?
It's not curl of A. This is A, right? So that's the that Lagrangian depends on A, even though A is not physical. And the question is, why is it like this? What is the argument? Why should it have this form? Exactly, that's it. From my point of view, as long as your Lagrangian produces the correct equation of motion, that's a good Lagrangian, right? But that's the physical thing. And here the equation of motion is Lorentz force is equal to Newton's second law. And as an exercise, if you have never done this, I think you guys are physicists, so this is not tricky. Solve Euler-Lagrange and find equation of motion. My experience is nobody can do this. I asked this in the exams, and people generally, they either, I also sometimes fail because if I'm not in the right mind, but since I did it a few times, I remember they generally mess up how to get the curl and magnetic field. If you have never done this, try it. I am not going to ask it, but in qualifiers and things like that, if people test you, if you have any kind of exam on the blackboard, people may ask you and you can put yourself in an embarrassing situation. That's okay, but the calculation is really simple. And this becomes like Lorentz force plus Newton's second. And philosophically, if you want, there's still like, right, this is the first derivative squared, right, dr dt, and there is like some potential, and there's like linear in A. If you want, this is sometimes what we call minimal coupling. There are some theories you can get like more complicated terms, but for real world applications, that's as good as you get. So there's the question of gauge invariance. Let's think about gauge invariance. So what gauge invariance says is like A is not physical. If you take A and replace it with A plus some gradient of chi, and phi, replace it with some phi minus 1/c time derivative of chi, equation of motion will not change, right? From that point of view, there's like so-called gauge degree of freedom. You can choose any gauge you want. So we want to do quantum mechanics, and quantum mechanics generally is formulated in terms of Hamiltonian. So you need to go from Lagrangian to Hamiltonian. So Hamiltonian is obtained as, okay, there is like so-called canonical momentum. So we define P as del Lagrangian del R dot, and it is going to give you M R dot minus Q over C, right? Is that Q over C? I think it's plus Q over C. This is plus Q over C times A. And Hamiltonian is H is equal to like Lagrangian depends on time derivative of R and R. Hamiltonian depends on momentum and R, right? If you want, Hamiltonian is kind of like a Legendre transform of Lagrangian, and what you find, okay, let me write it. So this is R dot P minus L, and if you do this operation, what you find is 1 over 2M. So this is P minus Q over C times A squared plus Q times phi. Sometimes, so this thing is shown with pi, and it is called mechanical momentum. How many people know this? Right? Yeah, okay, good. And how do we go to quantum mechanics? Once you write this Hamiltonian, you just promote P. So this, you just promote P to minus I H bar gradient, and you have the quantum mechanics, right? Now X and P, they have the commutation relations, and you can try to solve the equations like that. And what you have is Schrödinger equation, I H bar del T psi is equal to 1 over 2M P minus Q over C A squared plus Q phi psi. And the gauge invariance becomes, if you take A to A plus del chi and phi to phi minus 1 over C. By the way, I am using Gaussian units. That's why it's like this. If you use SI units, that's also fine. Use whatever you like the most. So this is del chi del T. In that case, wave function is going to change like psi times a phase, and that phase is x I q over h bar c times chi. Now back to Ginzburg-Landau. Ginzburg-Landau. So we had some gradient term. So this gradient term, we can relate it to be some kind of like P, right? And therefore, whenever we see P like object in the Ginzburg-Landau, we are going to replace it with P minus Q over C times A. And that will do it for most part. So a quick note, like Q is minus 2E for all known superconductors. And there's like a story in the book, and I think that's like a true story. So Ginzburg is a student of Landau, and he like was working with these equations, and he found that actually taking this charge to be minus 2E fits the experiments better. And then he like showed it to Landau, but Landau dismissed it. Actually, if you read the original paper, Ginzburg-Landau, they say that this Q is equal to minus E, and there is no reason to take it anything else. They say it in that paper. But many years later, after like BCS theory and all these experimental verifications, we know that it is minus 2E, right? So actually, but also Ginzburg account is not quite right, like because typically this E and 1 over m come together in the equations. If you take 2E, you also need to take 2m, right? That's why actually things do not change that trivially. But there is only one experiment, and it's like this flux quantization experiments. We are going to talk about it. That flux experiment gives charge to be minus 2E. But nevertheless, Landau actually is, he has other things. Like, for example, he also dismissed Abrikosov. Like, Abrikosov suggested, we'll come to that. There could be like a type 2 superconductors. But this is also, I think, real story. Landau dismissed it, saying that this is not physical, right? There's no point of studying that. But later, Abrikosov published it, of course, with the consent of Landau, and he got the Nobel Prize in, I think, 2002 for that. So then, this is the prescription. Now we can write the free energy. Free energy. So Fs, again, this, let me write it Fs minus F normal is equal to, so we have d cube R. Let me put like a big, and what we need to have is 1 over 2m. Previously we had the gradient, now we need to have this P minus Q over C A. This entire object is hitting on our order parameter, and we take absolute value squared. Right? Previously we only had simple gradients, and whether you put minus IH bar or not doesn't matter. Now we replace this with this better operator that has the correct gauge invariance. So this plus, the other terms are exactly the same. So A psi squared plus 1/2 B psi to the 4th. Is that all? So I have a psi fields, and what other things contribute to my energy?
You need Q phi as well.
Q phi?
Yes.
I mean, for the moment, I only like free energy with only magnetic field, because that's the thing we are going to do, right? We want to see the Meissner effect. Let's simplify it, and only with magnetic field do I have anything else to add to energy. Exactly, right? Magnetic field E squared B squared, right? It also has an energy, so we have to add this. And in the Gaussian units, I wrote it like del curl A squared. Good. If you want, so this first piece is so-called matter action, right? So this is matter field coupling to magnetic field, and the last one is electromagnetic action. So let's do it in 2 steps. First, let's minimize with respect to psi star. That's the simpler one. So what I'm going to do, okay, right, so there is like a gradient here, and one gradient is acting on psi star, the other gradient is acting on psi, but we can do the by parts and put both gradients on psi and leave psi star to be alone. If you take the functional derivative, psi star will drop out, and what you are going to find is 1, so this is 1 over 2m P minus Q over C A, this entire thing squared hitting on psi, plus these are trivial, right? We are just taking del f del psi star is equal to 0 and obtaining the equation. So let me push this just a little bit. A psi plus b psi squared psi is equal to 0. So this is the first equation. What else do I need to do?
With respect to A?
Exactly, yes, and that's the tricky one. We also need to minimize with respect to A, because A is also a field and we need to find the minimal configuration. For that, I want to write this. Let me write it Fs minus Fn. I want to write this like F matter plus F electromagnetic field. And F matter is the one with psi. F matter is equal to d cube r uh, 1 over 2m p minus q over c a psi squared plus a psi squared plus 1/2 b psi to the 4th. So you can see this piece is A independent, but there's nothing to do about this. But I want to open this up and try to see how it operates with A. Let me just open this up. This is d cube r. I wrote this like h bar square. Okay, let me write it in 2 steps so you can see. So this is 1 over 2m. So minus I h bar gradient, this is P minus Q over C A. This whole thing is acting on psi and the complex conjugate of this, right? So this is this thing times, okay, let me open up a little bit more space. And I'll take the complex conjugate like this. I'll put here star and I'll put this I. Good. I just rewrote this line. And this thing is equal to d cube r. So the first term, this is h bar squared over 2m gradient of psi squared. So this is also A independent, so it doesn't concern us. Whereas the second and third term, so this is plus this times this, right? So this is going to be I h bar over 2m gradient psi star, and this term is, I think, minus q over c a psi. Now this term times this term, so this is minus is going to be plus I, right? So this one is, I think this one is minus, or minus is here. So this one is I h bar over 2m. So this is A psi star Q over C. So this minus and this minus, they became plus, and this gradient is acting on here, del psi. And now last one times last one is going to be 1 over 2m q squared over c squared a squared psi squared. Now I do the functional derivative del F matter del psi star. So this term is not going to contribute. There is no A. Oh, sorry, this is A. So this is A. So this term is going to give me minus I h bar over 2m times q, right? I h bar 2m q times c. So this is del psi star psi plus 1 over I think this one I h bar q over 2mc. This is psi star del psi. And now this term plus, and 2 will come here. This is q squared over c squared a times psi squared. Let me check.
There's a 2.
So the 2, there's 2 here, I cancelled. Yes, thank you. And what is, maybe let me ask one more if Aliya Hoca showed it. What is the derivative with respect to A, right? Suppose you have like Hamiltonian or any kind of action and you take derivative with respect to A. It's going to give you an observable. So that's current, right? So if you want this del H, del A, or like any kind of action, let me write it F. Let me write it nicely here. So del F matter del A. I think there's also a factor of C. Okay, is minus J over C, and J is current. And from here we can write the current. We can read the current, and the current becomes J minus I h bar q over 2m psi star gradient of psi minus psi gradient of psi star minus q squared over mc psi squared a. You can see the London equation is also emerging from here, right? First, this thing looks like a probability current in quantum mechanics, right? Take any quantum mechanics book and look at the derivative of density, right? Psi star psi, use the Schrödinger equation. This is going to give you the probability current, which is exactly this form. But also, so if you replace this thing with NS, this thing's very similar to London equation, right? It's connecting to there.
Does the relation come from the quantitative relations?
So this relation? This one?
Yes.
So this is the definition if you want. If you go to Lagrangian here, right? Even in the Lagrangian, if you take the derivative with respect to A, you have Q times V, and Q times V is something like current, right? J in the general case, if you want charge current minus E density times V. If you are thinking about particle current, you can erase this. Anything with V is a current. And here in the free energy, we have this expression. But if you want, this is a standard definition in textbooks. You can use it as it is. So far we didn't optimize anything. So we wrote F. Okay, where is the F? We wrote F. Okay, where did I write it? Okay, here. We wrote F as F matter plus F EMI, electromagnetic, And then we take the derivative with respect to F matter, and we also need to take the same with electromagnetic fields. Let's also do that. So del, okay, number 2, minimize electromagnetic free energy, and this one goes like del F EM del A. So we need to take del A of this thing, 1 over 8 pi d cube R del cross A squared. Okay, after that I'll rearrange, and then you'll see things will look very nice when we are done with everything. So this one I want to write this epsilon ijk. So this is epsilon I j k del j a k. Everybody knows this, right? This is the curl, and since they are like power 2, I need to write the same thing, epsilon I l m del l a m. Now I have epsilon I j k, epsilon I l m, so I can write these two guys as delta. I set j is equal to l, delta k is equal to m, or minus delta j, the second one is equal to third one, j m delta k l. So everybody knows this, right? This is standard, good, very nice. And this thing means, this thing is this is equal to, this gradient is equal to del j a k del j a k del l is equal to j, a m is equal to k, j k j k j k j k, good, minus del j a k. Now l is equal to k, del k a m is equal to j, j k k j k j k k j. That's good. Now if I do by parts, right, I want to leave 1a alone so that I can take the derivative. So this is going to be ak del j squared ak, but because of by parts I need to put minus sign here, and this one is also the same, plus ak del j del k aj. Now this thing looks like gradient acting on A, and this thing is looking like A dot del dot A, right? So del dot A is scalar. If you take the gradient, it's like a vector, and that vector is dotted onto A. So everything makes sense. So this is plus, this is minus, and here we are using the right at this moment there's only, okay, this entire thing is multiplied with A. I can put it like this. Now I can take the functional derivative. Del f e m del A is now going to give me 1 over 8 pi and minus del squared A plus A dot del dot A. But because this derivative, or here this derivative can act here or here. There are two ways to act it. And if it is acting on here, I need to take the bypass. That's why, but it's the same term. That's why I need to multiply it with 2. That's why there's like a 4 pi here.
Second term, you have an extra A.
No, there's not extra, right? No. Oh, yes, absolutely, yes. Thank you. Yes. Thank you.
And in the bottom line.
What's that?
The bottom line, of course.
And the bottom line, AA, yes, this one is also gone. Yes, thank you. And this object is also something in the vector calculus. This is curl A. Good. Therefore, okay, long and a little bit tedious, but at the end what we have is 1 over 4 pi curl B. Good. Any questions? Now I want to put all of these together. What we need to do is del F all del A is equal to del A F matter plus F electromagnetic, and we should set this to 0. And what we found from here is 1 over 4 pi curl B. And what did we find from the previous one? The previous one is minus J over 4 pi. So this is minus, and J we defined over C is equal to 0. Therefore, what we find is which is basically Maxwell equation we found. Okay, so this is equation number 1. So equation number 2 is this J definition of J was equal to minus I h bar q over 2m psi star del psi minus psi del psi star. So these are like that, minus q squared over mc psi squared a. And the third equation is equation for psi, which is minus h bar squared over 2m del minus I rearrange iq h bar c squared acting on psi plus a psi plus b psi squared times psi is equal to 0.
I think we said A.
Oh, yes. I swallowed a here, right? So this is C. Good. Any questions? Maybe if this is too much, we can stop here. There's not much content, right? Like what we did is like we first considered the gauge invariance, and because of gauge invariance, it was reasonable to write an action like this, and we wrote the action based on physical arguments. And the rest was tedious derivatives, right? Taking the derivatives and be careful. We minimize with respect to psi star, and we found this so-called Ginzburg-Landau equation. We minimize with respect to A. There was like a lot of index gymnastics. We found like current, and we found del cross B. And at the end, we have Maxwell equation, definition of current, and nonlinear Schrödinger equation, but in gauge, in like a magnetic field. And next time, I feel like, I think hopefully we can use these and see how they manifest themselves in the experiment. Good? Thank you.